Center of mass calculation can get a bit complicated, but there are a few thumb rules that we can use to simplify it. And please note that there are certain conditions that has to be met before you apply it. Okay. So we are looking at center of mass. We are trying to figure out center of mass of rigid body with uniform density. Okay. So that's the condition. So there are a few basic ideas. You can take it as a not law exactly, but general observation. So first thing is, if we have an object and if an object has a point or a line or a plane of symmetry, I hope you guys understand symmetry means. For example, this structure, okay, this structure is symmetrical along this line. One more example I can give is kite. Actually, this is shape of a kite only. So if you have a kite and clearly this is not a line of symmetry, right? This is a line of symmetry. That is, if I fold it along this line, it will overlap. The structure will overlap. Is it not? So similar with that in mind, you can see this leaf structure has this line of symmetry. Somewhere along this line will be a center of mass. Okay. So along this line, exactly where that we don't know. Along this line will be the center of mass. Next, object with regular geometrical shapes and uniform density, the center of mass lies at their geometrical center. For example, we know that say a cylinder, or let me take a simple example. Say a book, okay? Book is a cuboid. So the thickness is the same and everything else is the same, right? Everywhere. So the center of geometry of this book will be along this line. And when it comes to the thickness, right? So if I happen to give it some thickness as well. So center of mass over this thickness, will be okay, somewhere wherein these 2 points meet. That's where your center of mass will be. Exactly. So this is the center of geometry. This is center of the geometry. Right? Geometry over here is a rectangle. And here too it's a rectangle. Right? It's a very simple thing. Where the diagonals meet, that's where the center of geometry is there. Your center of mass for such a case will be along the same line or along that point or at that point. Okay, so that's the second rule that we can think of or know. So we have a table with such facts. So if you guys want, you can pause and have a look. I'm not going to explain this. These are all the geometrical centers. There are many, of course. These are some of them. Right. One last thing. This is pretty important. The first 2 are kind of commonsensical. Third one is a bit complicated. Center of mass of combination of regular geometrical shape. For example, this structure is made up of 2 small discs. Okay. So one is a regular disc and another is a small disc. So the white space supposed to be empty. Okay. This is supposed to be empty. In this case, it is made up of 2 structures, 1 and 2. This is not empty. There are 2 structures. In this case also there are 2 structures, but yeah, there is overlap and stuff like that. So you'll be able to figure out such structures as well, center of mass of such structures as well, by using a small set of tricks. All we are using over here is simple center of mass formula, bit of coordinate geometry, and bit of symmetry skills. So how do you solve it? I'll give an example in the next video, but you should know that all of this can be found using simple set of rules. Actually, my intention for the last one is to give you guys this. So center of mass, when you have such a cutout, it would be total, or there's many actually, x total. Since it's uniform, I can just go with area of total times of center of mass along the x-axis would be something like this. Then the area of the cutout. I'll explain this. Let me write it first. Divided by, can you see that it looks similar? So area of the total minus okay. See, this particular actual structure is this. You have a disk wherein it has a hole. Okay, actually, let me make it a bit more clear. If I do this, it will be a lot more clear. Right? Does it make sense now? Actually, yeah, I should have done that before. Okay, so this is the actual situation. So I have such a structure. I want to find out the center of mass of such structure. So we know that such structure is made up of, this big structure T and this cutout structure C. So this is the cutout. And this is our removed, we can tell it as a removed. Let me use the simpler language. And this would be your the whole version. So AT stands for the whole version. XT is the center of mass of whole version along the x-axis, minus AC represents the area of the cutout version or the removed version, and XC is the center of mass of the removed version, removed part. And this is the same thing again. So this is to do with area of whole version. So we'll be doing this, guys. I'll be taking care of this. I'll be teaching you guys this. And X here represents X coordinate of center of mass of removed version. Okay. So such will be the rule that we'll be following. Very simple. I'll explain with an example. But yeah. So you guys have to know this. Copy all of this. We'll make use of it and we'll understand better. And there are many like this. I just wanted to show you guys an example. So there are many such rules and formulas. Not rules, formulas. So we'll be deriving quite a few of them actually. And yeah, this I'll be showing you guys an example. So for different combination, it gets a bit complicated for this third one. For the second one, it's a simple addition and stuff. For the third one, yeah, I will have to do it as a separate full-fledged video.